Thanks, Raviel, and thanks a lot for inviting me to to present on this topic. Since I would like to recruit contributors to it, so I'll go ahead and get started. I'm going to switch to slide show, so hopefully I don't destroy everything. Can everyone still see the slides and hear me speak?
It is working.
Perfect. Okay, I'll just jump to the next slide here. Quickly, just about myself. So as Raphael introduced me, I'm a software engineer at Ventana Microsystems. I show up in different places for RVI, different TGs and SIGs. Probably most frequently, I'm joining PRS and BRS, also the server SOC from time to time, and platform, server platform that is, and the hypervisor SIG. I also pop up on mailing lists. Since I do software, I show up in software such as Linux. Also, for that Linux work, I specifically KVM. I go into OpenSBI, QEMU not only for using it as a platform we can create models with for RISC-V platforms and devices, but also using it as a VMM, virtual machine monitor for KVM. And then kvm-unit-tests also is something I contribute to, and that's actually going to be today's topic. So here's the outline. First, we'll try to give a little motivation. I'll try to shed some light on the problem we're trying to solve with kvm-unit-tests at all. Then I'll introduce kvm-unit-tests for the purpose of trying to present it as a potential solution to that problem we're trying to solve. And then I'm going to switch into a bit of a demo tutorial mode, which hopefully will all work fine. It's going to be live command typing, which is always a bit scary, but we'll see how it goes. I wanted to do it in this format because trying to do screenshots, a bunch of screenshots of different command outputs or test runs and things like that is difficult to do since you have to cut a lot of context out to get it to fit. I also wanted to show that it's not that hard, that I didn't want to portray that it was a bunch of screenshots that, okay, here's how little bits of it look, but I had to run 100 commands in the background to make that happen. No, it's really just a dozen commands or so that I'm going to do, and we'll be able to exhibit the whole thing I want to exhibit. Then we'll summarize, and that'll be the end. So the motivation, what's the problem? Well, throughout the technical working groups that we have in RVI, we're writing specifications, and we're not only writing specifications, but many of those working groups are also trying to write test cases for the specifications. So I can think of a handful right now, which is PRS, which is doing the SBI interface. And I have that depicted on the right side just to make sure we all are on the same page for SBI. You can see SBI twice in that picture, once in between the layers of S mode and in mode, and another time between VS mode and the hypervisor. And anyway, so this is one area we want to have test cases. Another one is BRS is doing that. The server SOC is doing that. The server platform is also writing test cases for the different specifications that they're writing. So we need some sort of framework that allows us to test those functions that are being implemented to make sure that implementations, and there can be many implementations, right? We have a reference implementation a lot of times that we develop as part of the working group, and then other people, they can come up with their own implementations, and we can test to the same spec with the same test cases with some sort of a framework that we all agree upon using. So that's one reason. And then another one is ICE extension validation. So this is actually very similar in the regard where we want to, for example, have a new set of instructions that some ICE extension is introducing, and we want to make sure that they behave correctly on either a platform, like a real hardware platform that we're building, or even just on kvm-unit-TCG or some other emulator model where we want to first write that emulator code to make sure that we have a model that is functional, and we want to make sure it works according to the specification too. So when we use it for other testing purposes or building our software stacks, we can trust it to be representative of what we plan to build in hardware eventually. Okay, and also, of course, test framework is a good environment to have around when you're doing development and debug for other software components. You can just do quick and dirty little snippets of code in there, which represent a small part of a problem that you're trying to solve, and make sure at least that part's right, for example. Okay, so in that last slide, the sub-bullets were actually becoming a bit like requirements. They weren't, in fact, I'll just go back. So for example, the small bullets under the SBI heading, large bullet shows that we want to be independent of operating systems and bootloaders. And the small bullets under the ISA extension, big bullet, is showing that we want exclusive access to the platform and that we need to be able to run these tests in privilege mode. And we can't just accept some sort of a test framework that would only be limited to a single heart. It needs to be able to run on all hearts in the system, or at least a large subset of them. And so those are actually already requirements kind of being listed for what this framework should look like, not just motivation for it. And then here's some more framework requirements. Some of them you could maybe consider nice to haves or preferences, but I like to consider them all more or less requirements because one of the main things about a test framework that is probably one of the most important things about one is that it's easy to adopt and use and to apply in the different areas that you want to apply it. If it's clunky, if it's tough to use, or you have to rewrite code and recompile it on a regular basis in order to apply it to something, then it probably won't get used. Getting people to test at all is already kind of hard to do, and then and write tests and do the test. And so you want to try to make that runway as short as possible between hey, let's test that thing and oh, we finally tested it. So the framework should try to do that as painlessly as possible. So of course, the I/O would be required anyway without being able to output test results. We have no test suite, but inputting parameters is a bit optional. I mean, I've seen test frameworks out there where you need to actually fill tables of data with your test parameters, which actually get compiled into the tests, and then it'll run and it'll work just fine for that particular configuration. But if you want to do another configuration, you're going to have to go back and modify that table and recompile and everything else. So it's kind of nice if you can have that table or whatever parameters you need separate from the test suite and be able to input them. That way you can only compile once. You can move the test suite around. You can maybe leave it there if you don't plan to change it for a while, and just modify and change the inputs. Also, of course, it used to be easy to develop tests. If you're writing all your tests in pure assembly, then you're probably not going to write that many tests. You just don't have time, even if you want to. So it needs to be a higher level language, but it also one that people are familiar with is a good thing to choose. And when the language comes along with those the familiar language, those familiar APIs for that, those should be supported. Debugging should also be easy. Tests, especially tests that are going to run in S mode, privilege with exclusive access to the platform. You don't have a lot of environment there to debug with. I mean, you don't have. It's not like a user space program where you can just run it under GDB or something. So, to the best of the framework's ability. It should be able to show you where things have gone wrong, or give the developer opportunities to isolate where things have gone wrong as easily as it can. Then also, because we're going to be in privilege mode and we're going to do stuff with size extensions and other extensions, some additional API, unlike the familiar stuff like string allocation and whatnot that you would see for a user-space program, we're going to need to be able to install exception handlers, execute functions on other hearts, and synchronization and stuff like that. So there should be API for that as well, which makes that relatively easy to do. So I think I've more or less described in the last few slides that we need a framework and what that framework should look and feel like. And so now what I want to do is propose that we already have such a thing. It's called kvm-unit-tests, and I'll try to describe why I think it kind of fits the bill. First of all, it doesn't sound like it will from first read, because there's the KVM in there, which is indeed the kernel virtual machine. It was originally designed to be used for testing KVM. But the thing was, when testing KVM, to do that, the best way was to build a little tiny guest kernel and then do different actions inside that guest kernel, which would force the hypervisor KVM to respond and be able to test that behavior. So we already have a framework now that can run tiny guest kernels. And actually that framework has been evolving over years to not even require being in a guest anymore. It can actually run bare metal. So we can just launch it right from a bootloader, these little kernels, and now they're running without a hypervisor at all. And that makes them suitable for the type of testing we've been talking about, where we want to actually test an ICE extension on real hardware, or test an SBI call directly without any sort of intervention from hypervisor or anything else, but directly to in mode. And of course, we can test the SBI implementation of a hypervisor if we wanted to, because these tiny kernels can still run as guest kernels. Not a problem there. So also kvm-unit-test supports multiple architectures. It's been evolving. It originally was only for x86 KVM. It was actually built at the same time KVM was, which was originally only x86. But now it's been evolving to support several architectures, most recently RISC-V. All of these architectures are designed in their own ways to be able to boot Linux directly. ARM and RISC-V have particular specifications from Linux on what registers should have what, etc. The state of certain CSRs and things like that. And this unit test framework will, if that is abided by when you launch these tests, then this unit test will also run just like Linux would. Also, you don't need the specific Linux thing. You can have the EFI protocol for another way to boot. So you can boot directly from any EFI capable bootloader, which includes U-boot and of course UEFI. And RISC-V now also supports that. At the time I wrote the abstract for this talk, that had not been merged yet, but it was merged on Monday of this week. And then kvm-unit-test supports discovery hardware description through device tree. Also, there's some limited ACPI support in there for x86 and ARM. Not yet for RISC-V. It's somewhere on my to-do list. And so that'll also be there eventually. Of course, setting up the MMU, building page tables, things like that, and also preparing and launching secondary hearts is support that all the architectures have, including RISC-V. Limited IRQ control, controller support is something that RISC-V doesn't have yet. Other architectures do. that's also coming eventually for RISC-V. Of course, it would be nice to be able to receive an API or something like that for some of these tests that we want to write. So that'll be something we'll want to add. Okay, so now that I've talked about some of the features of of kvm-unit-tests, like what it can be able to boot on and then support. The question is, well, how does this look to a test writing, to a test writer, to a developer of tests? Well, to the best of our ability in the framework, we're trying to make it look like you're writing a C application. So nice and familiar to almost everybody. Where the entry point to a unit test looks exactly like a C application, exact same signature. In fact, we can even use git env to get environmental variables that could be provided. And then other libc functions, some of the most popular ones, are also implemented and supported. So when you write your test, you can kind of write it like you're writing a C app. Of course, you're not writing a C app. You're writing C code for a tiny kernel. So when you need the exception handlers and to launch tasks on other hearts and whatnot, then we have the API for that as well. I have a couple examples listed there in that first sub-bullet of the second bullet. And then there's also a bit of API added just because this is a test suite, and we're doing one of the main things we're trying to do is check if something works, and if it does, then report it or report the failure. Report skip is of course important because you want to be able to run your test on anywhere without having to be concerned that you're going to get false failures, false positives on a failure. You want to first probe to see if what you're testing even exists, and then when it doesn't, you can report skip. You can also report skip if you're missing some input from the user for configuring a configurable test. If you have a test that doesn't have all parameters hard-coded, and then you're missing a parameter, well, then it's a report skip because you didn't fail the test, you just couldn't actually run it. And then the framework also includes a bunch of bash scripts for doing some test execution, automation. It's written in bash instead of Python or Go or something like that, because we actually suggested it one time that we might switch to Python or whatever, but people are actually trying to put these test cases on embedded in embedded environments, and sometimes they want the scripting environment with it too. Sometimes you can't actually apply the scripts at all once you've ported to some embedded environment. But if you're doing, for example, tests of a hypervisor in an embedded environment, you might still want to run the scripts because now you have a usable Linux environment there with bash, so you can run the scripts. Anyway, but you wouldn't want Python in that environment, for example, so that's why it's bash. There is some documentation, which I have a link to on the last slide, the references slide, but it's really out of date. So this is maybe also on my to-do to finally update that at some point. Okay, so now this is the last one before we try to figure out how to go to a shell. I'll have to stop sharing this screen, I guess, and start sharing a terminal. Hopefully that will go all right. So on this slide, we see that this is how I envision or how I do it as well. The introduction of a new test or using it for whatever reasons. First, you go grab the code, of course, and then you go look at some other tests that's maybe similar. And a lot of that code you can mimic and can use as well into the new test. Of course, if it's really overlapping a lot, the test probably belongs in the same source file and share a lot of the helper functions, whatever. But that's actually not the important part for just getting things going. And then And then there's this just the build and run aspect of it. So it can be cross-compiled, of course. And then I think most would probably want to do their rapid testing of it. If QEMU supports this particular feature that you want to test, then you can just go ahead and do all your testing locally on your own notebook by cross-compiling and executing on QEMU a few times until you've kind of shaken out the bugs. Then when you're ready to actually test on a real platform, all you have to do is collect the binaries of the test and move them over to the target. This is actually target specific. I don't have any scripts for this, although maybe some generic helper scripts could be written at some point if we can find something similar there where people want to do the same thing. And then, of course, you boot and execute the test. It'll execute on boot. It's not two phases. It's just boot, execute. That's also target specific on how you're going to boot it because it depends on the bootloader. But if you plan to do it with the EFI built tests, then one obvious way to do it would be after you've been able to put the test into some file system, the UEFI file system, I guess FS, then you'll just boot into the UEFI shell and execute them from the command line. Okay, so let's see if I can figure out how to share my terminal.
While you're trying to share, there's a question in the chat from Alex, like, what is the difference for EFI development on KVM versus on board?
The difference between building it for EFI that will boot with KVM versus onboard? Did I understand the question correctly?
I'm not sure if that's build. So, Alex, can you clarify the question?
I can. If the question is, will there be a difference in these tests that are built to boot with EFI between if I was going to launch them under KVM or under bare metal, then the answer should be no. Ideally, there would not be any differences there. So if there are differences, then we need to figure out where that difference comes from. If it was a framework problem or a bad assumption or a hypervisor issue. So, but no, there should not be a difference. It should be just the same. So I think you guys cannot see that yet. Oh, because I haven't actually shared yet. All right.
Now I can see. Maybe you can increase the font a little bit.
Yeah. Tell me when.
That's good.
Okay.
Yep.
All right. So now the fun begins. So I do have commands already pre-typed in another window. I'll be copy pasting to hopefully avoid showing you how badly I type. So first, I just went ahead and to make sure I'm not hiding any rabbits up my sleeves, we're going for this from scratch, a brand new fetched repo. And you can, if I was a brand new developer for kvm-unit-tests, I'd probably hop in there and do an LS right away. You can see a couple of green things popping out saying what you should do next. You should configure, and then you should run the test. We can take a look at what configure offers. There are a handful of things there, notably that we can cross-compile, and a couple of different features can be enabled and disabled. Down at the bottom, you can see that the support for EFI building is one of those features. So we'll revisit that later. For now, we'll go ahead and build for RISC-V 64. We can actually built also for RV32. At this time, I think everything runs on both. At some point, there will be probably a divergence on what runs on 32 and what runs on 64, but we don't have much yet. It's newly introduced to RISC-V, so we're not there yet. Anyway, that was it. We built it, it's done. And so we need to run it now. Since we're going to be running it on my x86 notebook here, we're going to obviously run it on QEMU. And I already have QEMU in my path, which is 822. And yeah, you need a pretty recent QEMU. Not so much for the code that's being run in the tests, but because the test framework scripts have decided to try to compose QEMU command lines with some more modern QEMU aspects. So that's why. If you don't want to have QEMU in your path, or you're switching between QEMUs, then you can actually set this QEMU environmental variable to whatever path you want. And you'll see that there's a theme about this. Environment variables are a large part of configuring and controlling the test framework when you're using the scripts, that is. If you don't use the scripts, then do it however you want. In fact, just to kind of follow through with that thought, you can see that even just when we configured, we already started building some environment variables that we'll be using, but the scripts will be using. Anyway, since we already have a QEMU in our path and we don't have anything special we want to do at the moment, we just want to see what happens, we can go ahead and run. And we got passes, but we also see plenty of skips. So we can look a little closer. First of all, let's go ahead and look at the self-test thing, and I'll just explain why we even have this thing. So self-test output shows that here at the top, we see the actual command line we ran. And so you can see that if you didn't want to use the framework's bash scripts, you don't have to. You just need to compose these QEMU command lines yourself. No problem. We see that we're using the Open SBI, which is actually built into the QEMU. And here from this banner down, this is actually output generated by the test framework. We see a couple skips in there. We didn't do any environment parsing, and that's because we didn't actually provide an environment. Everything else looks like it worked fine. We can see that we did some secondary checks. We tested exception handling and things like that. And we can look at the code more in a bit later. But first, I want to kind of run through how we run stuff, so everyone can see what I'm pointing at and stuff, right? It's not like falling off the bottom of a screen or anything.
Yeah, we can see that.
Okay, good. My screen, it doesn't show everything, but mine's not the important one. Okay, let's see. So the other test we had there was this SBI thing. So this is the beginning, and it's very much beginning of the SBI test framework that we'll be building. It's the same looking stuff as the self-tests. Oh, and by the way, the self-tests, I forgot to mention, is there. It will evolve with the framework itself. So when we add some IRQ controller support or whatever, then there will always be a new test added there as a sanity check to make sure that the framework is doing what it's supposed to be doing. If all those tests pass, then we have some more confidence in our actual tests that we're going to be running. So here we are again. Now we're looking at the SBI outputs, everything below the banner, as I said before. Here we have a lot more skips, and that's because all of the parameters that we have for the SBI test so far are configurable. We don't want, if you switch your platform or your SBI implementation, then these parameters are going to change, or they could change. So you can't really have them just hard coded into the test. And this also gives me an opportunity to show how the environment variables work. So we can create a file, and this file name is arbitrary. It doesn't have to be called test in, and we can put environment variables in it. So kvm uses inventor ID 0. And then we can pass that environment into the test framework when we run through these scripts. And we see now that we actually got the expected variable there, or expected value there. And when it ran, and if we try to break things, then we can break things. So we can see that we failed this time to get the expected value. So kvm is got an inventor ID 0, the SBI implementation, which is OpenSBI in this case, properly exposed that to the test when the test asked for it, but we thought it was supposed to be 1 and we failed. So everything is working the way it's supposed to for a test suite. Then we can actually also just run the SBI tests instead of all of them, as we've been doing here. We're running a self-test every time in the same way. And we also can test with Rust SBI, for example. We don't have to use the exact same SBI implementation that's built into kvm if we don't want to. Once again, another environment variable type of thing. So let's see what happens when we give Rust SBI. We get the same failure, so that's good. Also we got the same skips and the same passes, and if we again fix this, we should get to everything passing this time, except for the stuff skipping. So Rust SBI has now been tested as well for this one simple test case. Okay, so now we've proven that we can do stuff under kvm. This is directly booting. It's with this -kernel command line option for kvm. It's actually nothing too magical. And it's not exactly representative of what you would probably end up doing when you want to run this on some bare metal environment where it doesn't support this Linux boot protocol. Instead, you'll probably use the EFI. So let's refresh our configuration and enable EFI. And now when we make it, everything is built again, but now in a way that it can be boot with EFI. And we need to do one more step, yet another environment variable. We need to make sure we have an actual UFI implementation, in this case EDK2, the RISC-V vert one, because we're still using the RISC-V vert machine type under kvm, since we're doing everything on kvm for testing purposes right now. And now we can go ahead and run it again. The run scripts will still work when we want to use kvm. There's no reason for them not to. So we still get the advantage of these run scripts, even with the EFI builds. And this allows us to do some rapid prototyping with EFI builds before you would move it to some platform. And so here I've run it again. Everything looks exactly the same, except for when we look at this output now, we can see this huge amount of blank space there. We also see up here, we've added some stuff to the command line. We've got our EFI there, and we can see also that it was running down here, and we've launched this test through that. So now this is still using the direct kernel boot, which is actually probably the only way that makes sense when you're going to use kvm anyway, since it's much faster. If you want to have a slightly more representative of a building for a platform for bare metal type scenario, then we can do yet another configure. This time we'll disable the direct booting that we do even with EDK2. And we'll run yet again. Everything still works the same in this regard, except for the fact something is missing. Yeah, I forgot that I can't actually pass in my environment in this environment, in this configuration. We would have to put the environment into the file system as well. So this one takes longer to run, which is why I think it makes more sense to use the direct when it's possible for testing purposes. But it still proves that everything's working. So now we can see here at the top, this is familiar. This looks like it did before, but we've actually gone ahead and created a DT that we put into the file system because we don't have the direct boot magic anymore working for us. And we could do the same with the environment variables. It's just not being done at the moment. And then we can see that we've actually gone into the UEFI shell this time. And the only reason we were able to run the test directly instead of going into the shell and typing the commands to run it is because we actually also automatically dropped the test into this startup script. So anyway, it still runs all of it the same as before. It's slower though, because we now are a little bit more representative of how it's going to look on the platform. So that kind of concludes how to run stuff. And so we should probably look at some code. So we can do a C-scope in case we want to jump around a little bit. And let's start with the self-tests, go in the same order we were in before. And so as I said, all these unit tests, they look kind of like a C app. They start with the main function. And they have some report API stuff allowing us to build these machine these parsable outputs, right? I mean, we saw there was always like a very pass and then some name and then another like prefix and stuff like that. That way you can actually dump the test results into some other script that will parse it without concern for having to change that script too much. In fact, unless it's an actual reporting of a real test, you should use report_info for just random messages. That way the parser, that'll have the info prefix, and the parser would be able to just ignore that. That way it can change randomly without upsetting a parser. Anyway, so this is just proving things like command line options work, environment variables work. SMP testing, it shows that we can launch a bunch of secondaries and that they all, became alive at some point. We have some convenience functions. This is exhibiting here, allowing us to iterate over those things, over those present hearts. Up here, we show how we're doing the exception check to make sure the exception handling is doing what it's supposed to do, or just forcing any legal instruction exception in this case, and then jumping past it. And that's it. So that's what self-test is up to. SBI, same start, the main. This one added a help text to help kind of educate people why they're getting skips. It tells you need an environment to actually do this type of stuff. And then there's, so far, out of all the SBI extensions, so far only the base extension has been implemented. So there are people interested in continuing this work though. So expect more to be there later. Up above, there's just these helper functions to help reduce some of the code bloat. It's very repetitive for each of these particular base functions. In fact, we could probably create another helper function or something to clean some of that up. But anyway, it's the idea is that you grab the environment variable and then you make the SBI call, and then you check to see if it matches the expected value. Quite simple, but does the job. Now, there's also the fact that not all tests are going to be part of some like SBI test framework, or they're going to be part of some other specifications set of tests that they want, but they're going to be kind of ad hoc or something that people need maybe to test while they're building supported to even QEMU-TCG, or they want to do some ICE extension tests, but just for like a one-off type of confirmation. And so maybe not everything will make it into the repo for tests. I have an example of that right now in my copy of this repo under a branch called xtest. And I'll show you that one as well. So this one I wrote because I was recently patching QEMU to support this accessed and dirty bit setting in page tables. And I wanted to make sure it worked the way I expected it to, and also then to test. And there was like 3 or 4 different ways it was supposed to work, and mutual exclusive and things like that. So I wanted to make sure it was all kind of ironed out in the end. And so I wrote this test just for that reason. I don't know if I'll ever want to merge it into the framework, but this is the type of thing that people might want to do. And then it would be nice if they would at least put it somewhere public, so code can be shared, people can get inspiration from it and stuff like that, of course. So anyway, this one is setting up these page fault handlers that it's going to need to prove that it got an exception when it was supposed to and didn't when it wasn't. And then there's also some funny looking stuff with the word hacked in there. And that's because we needed to be able to change OpenSBI's behavior in order to force different modes. And well, I don't want to go on a tangent here, but there will actually be an SBI extension called FWFT, probably for 3.0, which will allow things like this without having to do hacky stuff. But this is just kind of underlines the fact that kvm-unit-test is useful for these hacky things. You can, between hacking on the firmware and also creating kind of these quick and dirty tests, we can actually test these one-off type things. So the check here shows you, I'm checking the PTEs and stuff like that, making sure that the bits are getting set appropriately and whatnot, and things like that. So the other thing I wanted to demonstrate was this particular file is that it's not very long. It's only 154 lines, counting white space, and it actually tests a relatively interesting, actually 2 extensions. It tests both the SWAT-A and SWAT-U extensions, plus it checks QEMU's behavior from when it was first developed. So it's actually testing like 3 different behaviors, and it's only 150 lines. And so these tests can actually be quite simple to write. I'll go back to the slides now if I can figure out how. Yeah. So I should be back. I hope people were able to follow that and see all the stuff I was typing, and that it was hopefully somewhat productive. And now I'll just summarize. So I think we've shown, or I've tried to express at least, that the different working groups in RVI are in need of some sort of test framework where they can do the types of things I just exhibited in the kvm-unit-test can do, where there's no operating system involved. You can run it from different bootloaders, particularly if you build for the EFI build and you have a bootloader that is EFI capable, then it shouldn't be a problem. It should just work. And then the tests are, at least in my opinion, pretty easy to develop. And and so those are the requirements that we said we had, and the need that we set out to fill. And I think, in my opinion, kvm-unit-tests is able to fill those requirements. I'll also say it's actively maintained. At least I'm not the only one maintaining it in general. I'm maintaining specifically the ARM and RISC-V ports, and also the general framework. But there are other maintainers for the general framework and other architectures. Also, so we've already decided to start adopting kvm-unit-tests, at least for the SBI testing, and the RPMI as well. And so we'll see it hopefully grow over the next months. So here are some links for anyone. The one at the top is the one we cloned at first. The second one down is the one I just cloned now for that other test. I mentioned there was out-of-date doc. That's that one. And then the mailing list is where you'll send your tests and your patches and inquiries, or to me. So with that, I think I'll conclude.